I'd like to introduce you all to Greg Slepak of DNS Chain.
Thanks. And actually, I think I'm going to start off on the whiteboard. I really like the whiteboard. Is that all right? Yeah. How do you have the light? Okay, so this class talk is about internet security and securing internet communications. So how is that done today? What is like the primary way by which internet communications is secured? Does anyone know?
Certificate authorities?
Yeah, I heard certificate authorities, right? But I guess we'll go into that. But what's sort of the protocol that's used? HTTPS, right? And that uses another protocol called TLS. Recently, you might have heard that SSL apparently is dead. What that means is that the old version of the protocol powering HTTPS is deprecated. So I'm going to talk about HTTPS and how it works. And I'm going to also talk about specifically what the little lock icon in your browser menu bar is when you go to HTTPS : some website. So somebody mentioned certificate authorities. What are they? What do they have to do with HTTPS? What do they have to do with this lock icon? That's what we're going to get into. I'd just like to get a better idea of how much you guys know about all of this stuff. So can you raise your hand if you know what certificate authorities are, what their purpose is, and what they have to do with HTTPS? Okay, I'd say about, I don't know, maybe 4% of the class. So that's good, because that means that I get to explain. Okay. So the basic idea between internet connections, and I'll use Firefox because it's my favorite web browser. You have a website, so let's say we'll use Twitter.
A bird?
Yeah, a bird. Thank you. Actually, let's use a bird. What is the bird? I think it looks. It's got like a little tail and then.
Dinosaur. Nice wings.
Yeah. That's the Twitter dinosaur. So what we have here is we have essentially a piece of client-side software. So this is running on some kind of a laptop or an iPhone or some kind of device. And over here, this is actually another computer, a server of some sort. In between them, they have this, internet thing. Clouds, obligatory clouds. The idea of securing internet connections is making sure that when you exchange messages between these two devices, those messages cannot be tampered with, and nobody can read them. That's the idea. Nobody can read them except for these two endpoints. So that's the general idea of what it means for a connection to be secure. And how is this done today? The way this is done is that we rely the entire internet, basically, at one point in time, a group of people were trying to tackle this problem, and they had to figure out how to solve it. And they decided, well, we're going to create these entities called certificate authorities. These are authority figures whose job is to act as like a well, I guess an authority that vouches for the security of this connection. And we're going to limit their number. We're going to say that only certain people can be certificate authorities for the entire internet. And the way that that system progressed to this day is that, according to one survey, there's about roughly, and this number is somewhat disputed, but it's about, in total, a little over 1,000 entities, organizations, that are root certificate authorities and intermediate certificate authorities, have the power, I'll just draw them in circles here. They have the power to declare a connection to be secure. And every single piece of software that needs to make HTTPS connections, and that includes Firefox, and that includes operating systems like OS X, Windows, and Linux, comes shipped with a subset of these certificate authorities, usually on the order of around 200 or so. So Firefox comes with a built-in list of these are called pinned. The term is pinning. When you pin something in this lingo, what it means is that you take some information and you bundle it with the application itself. So in other words, every one of these certificate authorities has a certificate, which is just a public key. So a certificate, I don't know, I guess I'll draw it here. We'll just call it a cert. Has some information, like the name of one of these organizations. So a very big one is VeriSign. And then it has a bunch of other information, but the most important piece of information that it has is this thing called a public key. Show of hands, who knows what a public key is? Okay, I'd say about 40%. So this is a very important concept to blockchains as well, and to Bitcoin, because it's the same concept that's used to secure payments in the Bitcoin blockchain. It's this type of, there are two kinds of cryptography that are used primarily for encrypting information. The two branches of cryptography are symmetric encryption and, I think, asymmetric encryption. And this is, public-private keys come from the branch that's called asymmetric cryptography. So symmetric encryption is, so this is from asymmetric. Which basically means that there is a public and a private key. And symmetric cryptography just means that there's one key. Instead of two keys, there's one key. It's called a shared secret. So that would be like in one of the movies that you might see where somebody knocks on a door and a slit opens and they say, "What's the password?" That would be symmetric cryptography. Both people on both sides of the door know what the password should be. And you can, in cryptography, you can take that secret and you can use it to encrypt information. And then that same secret is used to decrypt information. That's very cumbersome, and it makes it difficult to secure online connections. So we can't really use that. Instead of using symmetric cryptography, we use asymmetric cryptography, which allows us to have two different keys. One of the keys, both of the keys are basically, they're a pair. They're related in some way. And it doesn't really matter which one is which. We just use one in one way and another in another way. One of them we declare to be the public key. And this is the piece that we don't care to be secret. It's something that we can share with anyone. And this is the part that's included in certificates. The other piece is called the private key. Now this is also relevant to Bitcoin payments, because when you take a public key I don't know, I guess I'll go over here. I'm running out of whiteboard space. When you take a public key and you put it through a hash function, you get what's called a fingerprint. And this hash function, in the case of Bitcoin, is SHA-256. So when somebody sends you a payment via Bitcoin, they send it to your public key fingerprint. And I guess you guys are, show of hands, who's familiar with that concept in Bitcoin? Okay. I figure everyone here is familiar with it, and those who didn't raise their hands are just being lazy. Okay. So what's useful about this public-private key cryptography and why it's useful for secured internet connections and for securing Bitcoin payments is because if somebody wants to send you a message that they want only you to be able to read, what they do is they encrypt it. Let's use a function called M, and they encrypt your message. Let's call that M, and they encrypt it with your public key. And then this, we'll call D, or, well, yeah, D for data, encrypted data. And if you want to get M from D, once you receive D, you just call this encryption function again, and you pass it this time D, and instead of your public key, you put in your private key. And it's called private because you're not supposed to share it with anyone. If you share it with anyone, then those people will also be able to read the messages that are being sent to you. And that sends you back your M. So let's return back to these CAs, is the abbreviation for them. The most important part of a certificate, again, is the public key. All the other information here is mostly extraneous, not super relevant. Your browser ships with a list of these public keys. Remember I said about 200. Now here's sort of where the trouble starts. The way that this system is designed is that, if these were apples, we've got like a basket of fruit. These are all very tasty apples. And every one of these apples has the ability to make your browser show this lock icon. There might be an apple down here that's got like a worm in it and some flies. And it smells. And it's kind of like, I don't know if you've ever seen moldy fruit, but it's sometimes can be quite unpleasant. They sometimes excrete liquid around them. And it just takes one rotten apple to undermine the security of every website on the entire internet. So to put that in context, would you trust me to secure your Wells Fargo internet connection? Most of you don't know who I am. Well, how many of you know who these certificate authorities are? How many of you can actually name some of them? Well, let's name some. Not you. No. Except for you. Yeah. Komodo is one.
Let's Encrypt.
Let's Encrypt will soon be one.
Soon.
Yes.
DigiSign?
DigiSign? Yeah, I think so. You mean DigiCert? Yeah, right. DigiCert. And DigiCert I think was killed because they were one of the rotten apples.
Yeah, and then there's VeriSign.
There's VeriSign.
Number of Verisigns.
Yeah.
Oh, it's good.
Yeah. And actually, I'd like to show you guys some other ones here. We go to blog.okturtles.com and we go all the way down to the bottom post. I've got some other ones here, and let's make them big. So here's the list on OS 10 of these certificate authorities. And as you can see, It's a very long list, and there's, like I said, about 227 of them. So I asked the question, are these friends of yours? Do you trust them all with your data? And really read through this list. How many of you can pronounce that?
Jerky.
Like, can I ask a question though, relative to the point that you're making
Sure.
about the 1200?
Yeah.
Is there, because they are a standard by which all the standards actually achieve? So even though there's 1,200 of them, there could be 12,000 of them. To the extent that there is a minimum standard that they all reach, then in effect, you know what I'm saying? So
Yeah,
is there
there's
something
a
there?
rule.
I mean,
There's a list of guidelines that you have to adhere to and prove to someone that you adhere to them to be able to become a certificate authority that's included in a web browser. And you can actually make your own certificate authority. There's nothing preventing you from becoming a certificate authority. The difficult part is getting people to trust your certificate authority and to ship them with your operating system or your web browser. And so the answer to your question is yes, there is a standard and there are guidelines that these organizations and entities have to adhere to. But that doesn't, that's kind of like a Band-Aid on the situation, because we know that even the US government, and the NSA can get hacked. And these are like, the best and the brightest of our, recently there was this huge hack that was all over the news where basically all federal government employees had all of their social security numbers and all of this other information, including all of the employees who had security clearances and information about that, all of that information stolen.
Do you have an example where actually, because of the certificate authority was compromised?
Oh yes, yeah, there's plenty of examples of that. And actually, the worst part of it is that these examples that we hear of are most likely a very small fraction of what's actually going on, because it's very difficult to know in the way that the system is designed whether there's what's called a man-in-the-middle attack taking place. In other words, whether a certificate authority issued a certificate for a website like Twitter.com that it wasn't supposed to. Because the way that this system is designed is that if any one of these apples vouches for the security or creates a certificate for any website, then that is legitimate.
There's also the other side of the problem, which is take the least financed of any of those CAs, which means they're probably in the least redundant facility and such. You corrupt the BGP routing, which right now is not properly secured, so that it all points to someplace else. You do a few other games and tricks. You can temporarily subsume that role in a fashion where now you can attack people that they trust. And so there are ways, it's kind of like that have nothing to do even with crypto, just using other ways to break into things.
So you'll just say that you're Twitter, but actually you're not Twitter. You just change in your routing the data to not.
Yeah, well, let's show how a man-in-the-middle attack actually happens. So what is a man-in-the-middle attack? A man-in-the-middle attack is when you got like, a man in the middle here, through which the connection is traveling back and forth. And he is able to decrypt and re-encrypt the communication on the fly. So what he does is he gets one of these certificate authorities either to knowingly or unknowingly create a certificate. And remember, there are many ways to get a certificate for a website. One of these authorities does not have to become a rotten apple for it to sign a certificate that it shouldn't sign. They can be hacked. They can be socially engineered. One of their employees could go away with the private key and share it with somebody, either intentionally or unintentionally. There's so many ways, and it can happen. It just needs to happen with the weakest link. So, you know, like I asked you earlier, do you trust me to secure all of the internet connections on the planet? I think you'd be crazy to. If you'd be crazy to trust me to do that, does it make any sense to trust people that you haven't even met in person to do that? And to trust people that you don't even really know who they are? And not just them, but anyone who can manipulate or hack them. And that's who you're trusting in the system. You're always trusting the worst kind of, like, you know, the weakest link. So this man in the middle gets one of these, oh, I see your hand again. This man in the middle gets one of these certificate authorities to sign off, to use their private key to create another certificate that says, you know, this certificate belongs to twitter.com. And then as you connect, you know, he has control of the network. He's like sitting somewhere between you on a router, between you and Twitter. He sends you his fraudulent certificate. You send him data thinking that he's Twitter. He decrypts it because he's got the private key for that. Then he re-encrypts it with Twitter's public key and sends it off to Twitter and just, you know, relays this back and forth. So, okay, now I'll get to your question.
Yeah, so you made it sound like the weakest link.
Sorry, could you speak up?
You made it sound like the weakest link could destroy the entire network. But let's say Twitter uses Komodo, and one of the smaller companies is hacked. Would that affect Twitter's traffic?
Yes. So this is another point to keep in mind, especially when you're shopping around for SSL certificates. There's a lot of companies out there making money off of this system, and they will charge different rates for different kinds of certificates. There are some certificates that you can pay for that cost a few $100s, I think, per year, maybe more. That will change, you know, this little part of the web browser from just like regular to green or something like that.
Oh, the EV sort of thing.
And there are studies that show that users absolutely do not pay attention to this. So they will not notice if instead of you know, it not being green, there's just a lock icon or something like that. It totally doesn't matter. So my advice to you, if you're going to be getting an HTTPS certificate, don't pay for insecurity. Get the cheapest one you can find, and the cheapest one is absolutely free. And there's an existing company called Start SSL that will give you free certificates, and that's who you should get them from. Because paying any more than that, you're basically being ripped off in terms of security. And soon there will be Let's Encrypt. Also, they will be offering free certificates. And this system is problematic for many reasons because, you know, even if you have free certificates, if everyone is going to just one of these entities, then the security of the entire internet rests with that one entity, effectively, basically. And you can have censorship problems, and you can also have problems with, like, well, you know, this is a multi-billion-dollar target, you know, at that point. And it's unlikely that a multi-billion target is going to be able to prevent its private key from being hacked. Very unlikely. So I'm here to talk about a solution to this system, an alternative system. And that system comes from the world of blockchains. So let's erase the bad apple. And let's quickly go over how blockchains can address this problem. So, as you all know, or should know, a blockchain it is basically effectively a chain of blocks that's secured cryptographically. And in every single one of these, in Bitcoin, for example, there's a list of transactions. Who knows what the very first Bitcoin fork is? Was?
You mean?
Namecoin, right. So the very first fork of Bitcoin was a blockchain called Namecoin, which is still around to this day and still one of the most valuable blockchains out there. as far as market cap goes. I think it's like hovering around 8 or something like that. Modify Bitcoin to introduce a new transaction that allowed you to register domains on the blockchain. So one of these, if we zoom in, is going to say, register d/okTurtles. In Namecoin, they have namespaces, different namespaces, which they define as, they use a letter prefix and then a slash. And then these get mapped, so d/ is the canonical Namecoin domain. So this gets mapped to okTurtles.bit. So once somebody registers a domain in the blockchain, no one else can register that unless it expires. What blockchains kind of introduced for the first time in sort of internet history was this concept of ownership of digital information that did not really exist previously. I mean, you had things like GPG, which could sort of allow you to prove that you signed a message and therefore kind of owned it. They were cumbersome. You would have to, you had this problem called Zukos Triangle. And what Namecoin did was it solved this conjecture. Zukos Triangle is named after Zuko Wilcox. And it states that in a naming system, you can have only 2 of 3 properties. It can either be secure, decentralized, or human readable. So you can have only 2 of these properties, but not all 3. And then some people started thinking about it after Bitcoin arrived. And they thought, well, could it be possible to use the blockchain that powers Bitcoin and use it to create a naming system that has all 3 properties? Where you can have this one database, effectively, that's shared across the entire planet, so that no matter where you go, and you ask for okTurtles.bit, you'll get the same information. That's the decentralized part. And no matter where you go, you can talk to the website for okTurtles.bit without a man in the middle. That's the secure part. And you only have to remember okTurtles.bit, not a fingerprint, which is, if any of you have ever used a Tor browser, how that works. It's like some unreadable mess followed by .onion. So Namecoin made this possible. Now, the problem with Namecoin is that even though it makes it possible to have websites that are secure, decentralized, and human readable, and that are man-in-the-middle proof, they block all man-in-the-middle attacks that are non-fundamental. What I mean by that is that you can still man-in-the-middle the connection if, for example, you were able to obtain or hack the private key of the owner of the domain, or if there's some sort of bug in the cryptography or in the implementation. Those are all fundamental attacks that can happen on any secure messaging system. These other attacks that I discussed, they're not fundamental. They're design defects. The problem with Namecoin and blockchains in general is that they're very difficult to run on laptops and mobile devices. And so you can't run a Namecoin full node on your smartphone and connect to okTurtles.bit. It's too resource intensive. It uses too much RAM. It uses too much CPU. It uses too much hard drive space. So DNS Chain is the project that we started working on at okTurtles, which is very simple. It's basically a proxy to a blockchain, a trusted proxy. So let me erase this part right here. So you've got a computer that you trust. And it's running two pieces of software. One is Namepoint, and the other is DNS Chain. And this is a server that's running 24/7 and has the resources to run this. And then you've got devices that talk to it, like a smartphone, a laptop. And these connections, they are man-in-the-middle proof because they are secured. These devices have the public key of this DNS chain server pinned in them, just like we use the pinning with the certificate authorities in web browsers that I raised earlier. So these devices know, in other words, what the certificate should be, so they can check and verify it. Now, there's still a problem with this system. The problem is that if you try to scale this to the size of the internet, you're going to end up in a situation where some of these devices are going to end up trusting DNS chain servers that they don't have good reason to trust. Because not everyone, at least today, is able to run their own server. And not everyone is qualified to run their own server securely and administrate it. And not everyone even has a friend who can do that for them, or a trusted organization. So that brings us to thin clients. Can we get the... So, this is where we're at right now, is using this concept called thin clients. And, let's see. This is probably the key sentence here. So this is talking about what I was just saying, is that man-in-the-middle proof proxies, that's that trusted DNS chain server. They're a great way to address the problem that blockchains are difficult to run on end-user devices. But they don't scale well, so we need what's called thin client techniques. And a thin client refers to software that downloads only a portion of the blockchain. So, although the end-user software ends up not having the entire blockchain, it's still able to, on its own, with fairly low resources, verify the validity of the connection. Not as well as a full node, and sometimes you can get it to be almost identical with a full node. So the existing method for this was called Simplified Payment Verification, SPV. But that may not be the only way to do a thin client. And so we have to sort of sketch out what the map of thin clients work on. Like, our work right now is about developing a generic blockchain agnostic thin client protocol that supports different techniques and can support any arbitrary blockchain. And so one of the things that we did was we developed a new thin client technique called proof of transition that's pretty much as secure as standard SPV, and it has some different properties. And this was done, this is sort of the picture that I showed you earlier. This was done to help us sketch out this map, to understand how different thin client protocols can be, because if we understand that, then we can understand how to develop a generic protocol that can support arbitrary thin client techniques, and even ones that have yet to be invented. How am I doing for time? Good? I can keep going? All right, let's go back to the whiteboard. I'm going to talk about thin clients now. And Actually, I don't know. Do we need to take a 5-minute break, or should we keep going? Okay. Okay.
Can you explain a little bit what DNS Chain does on top of Namecoin?
Yeah, so on top of Namecoin, DNS Chain provides a RESTful API to access the blockchain. It looks like something, if you request, you call get, you make an HTTP request called get the name of the blockchain, and this can be anything, so it could be Bitcoin. Well, let's say we call Namecoin. And then we call a resource, so key, we want to get a key. And then we specify what key we want to get. So we could say D, and then we URL encode it. How do you do that? Like 2F or something like that. okTurtles. And you call this over HTTPS, and it sends you the information that's in Namecoin. And it just makes it user-friendly. But right now our focus is on removing DNS Chain from the picture. Because that's the purpose of a thin client protocol, is to reduce the amount of trust that you're putting in these kinds of proxies. So that you can use a DNS chain server run by some random person and not necessarily have to trust them and still use it to secure your internet connections. So, but I'm going to erase all of this, and we're kind of going to go off back into Bitcoin land for a moment. And we're going to talk about how Bitcoin traditionally does thin clients. And again, so sure. What are some thin clients that you've heard of, that you know of?
Well, we've all used some thin clients on cell phones, like some SPV clients on
Yeah,
cell
so what are some
phones.
SPV clients that you guys use?
Electrum.
Electrum comes to mind? What else?
Mycelium.
Bread. Not bread.
Bread, and what was that on?
Mycelium.
Mycelium? Right, I've heard of mycelium. So if you're doing any kind of blockchain-y stuff, especially if you're creating a company that provides people with access to a blockchain, my recommendation, if you haven't looked into it already, is to look into thin clients and see if you can use them as part of the service that you offer, as part of the app that you offer. And although it may require a little extra effort, and might not even require that much because there's a lot of code out there already, it nevertheless will add value to your company. Because you're going to have competitors out there who can say that, well, our security is better than yours. Whereas, with this company, you have to trust them to not lie to you about, what the blockchain actually says. And you want to be a good member of the whole blockchain ecosystem. And to do that, the whole idea behind blockchains is decentralization. And so adding these third parties and kind of centralizing it kind of goes against the philosophy of what blockchains and decentralization is about. And that can result in problems, such as censorship and abuse of power and things of that sort. And it can also remove value, because if you want to compete with PayPal, for example, you want to be able to tell your customers that they can trust that you're not going to suddenly freeze their assets because you don't like some of the things that they're doing because you are have religious objections to pornography or something along those lines. So blockchains offer a good way to compete with companies like PayPal. But if you just do them in a PayPal-like way, you're not really offering anything new. So let's go back on track and talk about SPV and how you can restore your customers' trust in you by making them not have to trust you. It's kind of paradoxical.
And what's SPV again?
Simplified payment verification, yeah. So in Bitcoin, you again have these blockchains, or blocks that are chained together. And they've got transactions, but these blocks have something else. Every single one of these blocks has a hash in them. And these are also chained together. So it's a smaller chain within the bigger chain. Does anyone know what I'm talking about here? You can just like say it. What are these things? What am I getting to?
The transaction.
These are the headers, yeah. And what's the most important part of the header for SPV?
The entire,
Come on.
which is hashing
No.
translations.
No, it's, okay, this is called the Merkel Group. So the Merkel Group is associated with, I believe, the list of transactions for every single block. And what it is that it's just a hash. And the way that, so this is a Merkel tree. Let's do a quick review. So Merkel tree sounds like it's some fancy, complicated data structure, but it's really simple, believe it or not. All it is a kind of a binary tree. And at the bottom row is the actual data. So here, this is the list of transactions for a given block. So this, let's do a mapping. So like these are the same thing basically, and these are the same thing. And if I'm butchering it, please let me know. But I think this is how it works. So a full node has to keep track of all of these blocks and all of the transactions. A thin client does not. But a thin client has the ability to verify whether a transaction has been accepted by the blockchain. How does it do this? Well, these headers, these are called headers, as someone pointed out earlier. They're about 80 bytes, I think. I think they're about 80 bytes in size per block. And what thin clients do in SPV is they download the header chain. So they go out to the network, and they can do this via the actual Bitcoin network or through some trusted proxies. And they ask them, give me the header chain. And how does it decide whether or not the header chain is accurate or not? It does it in the exact same way that Bitcoin does. It goes by the length of the chain. So the longest header chain that they receive, they consider to be truth. And that's exactly what Bitcoin does. The longest chain that any Bitcoin full node sees, it considers to be truth. And if you hear that and you're of a security mind, you might already start having some alarm bells going off in your head. Because if a man in the middle can prevent you from seeing the full chain, then they can prevent you from seeing essentially the truth. And there's actually no real way around that. This is like a fundamental problem of censorship. If North Korea's internet is cut off from the rest of the world, well, there's really nothing you can do about that, except try and get that information to them through some hole in their firewall. But if a thin client and a full node are able to receive, here's the value. The value of Bitcoin is that they memorize these things. So even if a man in the middle comes in at one point in time, it's really hard to prevent thin clients and full nodes from seeing the full chain. Because it's kind of hard to keep track of these devices that are, like right now, my phone has been going through several networks as I made my way here to meet with you today. It's probably been given multiple different IP addresses. And when I go home, it connects to my Wi-Fi router at home. And then all of a sudden, instead of going through AT&T cellular network, it goes through Sonic, which goes through AT&T. So AT&T really didn't like me. They could technically prevent me from seeing the full Bitcoin blockchain. But say then I connect to some other network that doesn't go through AT&T. Then all of a sudden I can memorize what the actual full chain is, and I can know that someone's lying to me. So a thin client downloads the header chain. Truth is equal to longest chain. And they can tell if a transaction was accepted by the network. Network/blockchain. How do they do this?
Just interrupt for
Yeah.
a second, without going into a lot of detail to take up a lot of time, could you talk a little bit about truth equals longest chain?
What else?
What do you mean?
Well, I was just talking about that, so what else would you like me to elaborate on?
What exactly, so the longest chain concept, what, I mean,
In
why the
proof of work.
why the longest chain?
Why the longest chain?
Yeah.
That's a good question. So, have you guys not covered that in this class? I mean,
It
this is
has
like a-
been, but I think it wasn't covered as thoroughly in this class as it should have. I mean, basically, what he's talking about is the miners, when there's a conflict, they basically go off and start doing different chains. And eventually, one chain's going to be longer than the others, and that basically wins. And then all those on the short chain are not valid and aren't part of the truth.
So when Satoshi invented Bitcoin, he came up with this concept called proof of work. That was sort of his brilliant idea. That's what Chris is talking about. That's where the term mining comes from. Mining is essentially spending energy through CPU cycles or GPU cycles or ASIC cycles to take lists of transactions and push them through a hash function. So let's do a quick overview of proof of work, which is abbreviated POW. What a miner does is it sits there with a baby, no, not even a baby, not even a fetus, but more like a sperm and an egg of a block. So it's not really, it's like an ephemeral block, hasn't really been blockified yet. And it's receiving transactions, new transactions, that haven't made their way into the blockchain yet. You know, these are people who are saying, I want to send my grandma 20 Bitcoins because I love it. So what they're doing is they're putting this thing through a hash function, which I mentioned earlier was SHA-256. And this spits out a hash. So, okay. And what Satoshi said was, look for the zeros, my child. We want to find the hash that has 5 leading zeros. And if you find the hash that has 5 leading zeros, you've given birth to a block. And everyone can verify that. This is a very expensive. Find this hash, it's very time consuming. But to verify that you found the hash is instantaneous. And the number of leading zeros is called the difficulty level. And this gets set by the network in every block. And it's adjusted such that the blocks are minted globally about 1 block every 10 minutes in Bitcoin. So if blocks are being created too fast by the network increases the number of zeros that you have to find in this hash. If they're being minted too slow, it decreases the number of zeros because it becomes easier to find this hash. And this creates a random stochastic process around the entire planet so that these miners are kind of geographically distributed almost randomly, except no longer because they're in China now. Because China's got all the big mining rigs. That's another topic about the centralization of the blockchain and how to deal with that. But that's for a different lecture. So, anyway, once you've got a long chain of these blocks, what this chain represents, to answer your question, is this spent energy. So when people talk about Bitcoin as being wasteful, there's actually somewhat of a naive understanding of Bitcoin. It's not true, to be perfectly blunt. every single payment system and every single security system requires energy. I mean, we have locks on doors which work with the mechanical key, and those locks have to be built by either people or machines, and energy has to go into that to build that lock. We have gates that open automatically, and they require power to power them. And we have the plain old ordinary US dollar and gold bullion being stored in vaults, and those need energy to protect them. And you can actually calculate how much energy goes into this and see and try and compare whether it compares with the amount of energy that's expended by CPUs to secure the Bitcoin blockchain. And we know how much energy goes into the Bitcoin blockchain. It's about 1 power plant, I think, was the last calculation. Something along those lines. And you can also figure out, how much fossil fuel has been used to carry, bricks, trucks throughout the world to transfer gold and cash and all of that. So all payment systems and all security systems require energy. So this energy isn't being wasted at all. It's being used for a very valuable purpose, which is the security of the Bitcoin blockchain, which is where it derives its value from. So if anybody tells you that Bitcoin is wasteful, you tell them what I just said. And there are other ways of creating a blockchain called proof of work, which don't use CPU. But there they have some other problems. And their applicability may not necessarily be a global currency system. Because in proof of work, you have essentially rule by the rich or rule by the stakeholders.
You mean proof of stake?
What's that?
You can see, I keep hearing proof of work. You mean proof of stake?
Yeah, in proof of stake. Yeah, sorry. Yeah, so in proof of stake, you have essentially what's kind of a rule by the rich. And some argue that a very similar thing is happening in Bitcoin because you have these rich people who are buying these mining rigs, and then they are effectively the stakeholders. So they could be in some way equivalent, but it does kind of require extra resources. And the two properties are different. Like you can, for example, tell in proof of work whether you're cut off from the network simply by if you suddenly see a decrease in the difficulty. So you can actually detect censorship. Like if you're cut off from the network and you suddenly start getting blocks with very low difficulty, your suspicions, like you should have a client that tells you about that. It should be like a red flag. Uh-oh, I might be like suddenly, I was seeing blocks that must have been generated by like 800 terahashes per second, and all of a sudden I'm seeing them being generated by like 0.5 terahashes per second. You're being censored. You've just been cut off from the blockchain. If you're developing thin clients or wallets or full nodes, like do that, please. Tell users that. So the length of the chain represents the amount of work that went into securing it. And that's why it's called, that's why Bitcoin considers it the truth. And as long as honest nodes and miners control the network, then Satoshi considers the chain to be secure. So does that answer your question?
So there's shorter chains that get created during the mining process. And since there are multiple chains out there, the entire Bitcoin network looks to the longest chain to say that's the one we're going to use.
Right. Well, it's not profitable to mine on the short chain. You want to, because the rest of the network isn't going to accept it.
Right.
So if you want to try to outcompete the rest of the network, then you're going to have to get more CPU power than the rest of the network. And you can, and this is called
It's not profitable because there's not,
you could technically do that if you're like a government organization. These are called 51% attacks, and they happen on all blockchains, so they can't happen on all blockchains. But they, in fact, did happen. There was an organization called Ghash, which outsourced its mining, and they, for some moments, got more than 51%. Yeah.
But I think also, two miners could chance upon a block at the exact same time, and then continue, and whoever gets the longest, that block is therefore orphaned. And so it's by accident. So it does happen quite a bit.
It depends on network propagation delays. So a lot of the big miners, they want to be really well connected to like a bunch of different Bitcoin nodes around the network, so that when they find a block, they can get that block really quickly to others. Because if they do it slowly, then a competing miner might get their block first, and then all the effort that they spent in mining that block would be wasted because it would be orphaned.
It doesn't necessarily mean it's that shorter chain is bad or not trustworthy or has bad transactions. It's
Right.
just, basically it's a timing issue, right, is what you're saying?
In some ways, yes. When blocks get orphaned, usually it's not because of any malicious reason.
Right.
Yeah. Okay. 10 more minutes? Okay, I'll wrap it up. So, get back to SPV. If you're given a transaction and you want to know, using a thin client, whether or not the blockchain has accepted that transaction, what you do is, let's say we were given this transaction. You were given this transaction, you know that, you know this. You know this because you downloaded the longest header chain. You know this because someone told you about it. So how do you get from here to here? Notice something really cool about this. So the way Merkel tree works is that to create one of these nodes, you simply hash, and like at the bottom here, I don't even know, they could be like many children instead of two, but let's say that it's a binary tree. You know, every node has only 2 children at most. You take these 2 transactions and you hash them. And then this is a hash. And here you do the same thing. You take these 2 transactions and you hash them, and you get this hash. And then you take these 2 hashes and you hash them, and you get this hash. And then you take these 2 hashes and you hash them, and you get this hash. So, given this tree, how many nodes do we need to verify that this is part of this tree? You just shout it out. 3. Third time's a charm. 1, 2, 3. Right? You might. I don't know if you need to be told about. I don't think it even matters whether you know this thing or not. I think you can just be told this one, or maybe you do need to be told about that. I don't know. I'm a little tired right now, so I'm not going to even answer this. But once you have this, is it 3 or is it 4? Maybe it's 4. I think you need this one too. Sorry. Whoever said 4.
It's okay, dude.
Yeah. Sorry. Tired. You have this one, and this one, and then you get the Merkel Group. But notice that we didn't need all of these, and we didn't need all of these. And that's why it's called a thin client, because the full nodes have all of this information, and thin clients don't. So they're much more resource friendly. Proof of transition, which I don't have time to get into, is just another. Actually, I think kind of the strategy is very simple. When you have a when you visit a website, you're told the transaction that the website was registered in, and you're also told the most recent value, the most recently updated value. You ask that from 2 different trusted proxies, and you verify that they match, 2 or more. So then you establish the validity of these transactions based on consensus. And from there on, you can prevent lying. Because like if your DNS chain server gets hacked or something like that, you can detect it. Because what you ask is that, you know, if they tell you that the value is now this, you simply you memorize this value and you check that the signatures eventually lead to this. The signatures on the transactions. And that's it. That's proof of transition. Okay, any questions?
You're developing a protocol, a thin client protocol?
We have defined a thin client protocol, and we might not even develop it. It may or may not be developed. The purpose of it was to build out that map, to know, and I think since we published that, somebody else brought a 3rd thin client protocol to our attention that we're going to analyze as well. And once we know what they all kind of look like, we can develop an uber thin client protocol that's flexible enough to like support all of them basically, and future ones that we don't know about. That's kind of the purpose of exploring thin client protocols, because if you only know one, you might not necessarily be able to develop a protocol that can support others. And why are we doing this? The reason is because we want to develop, we want to make it easy for end user devices like this to access information, not just in Bitcoin, not just in Namecoin, but in arbitrary blockchains, and do it securely. And do it in a way that doesn't run down the battery of this, or make it impossible for these devices to do that. So that's why we're doing that. And why make it agnostic? Why not just focus on Bitcoin or focus on Namecoin? Well, because to do so would be to create, it would be kind of like short-sighted, because we don't know whether Bitcoin will be abandoned, in 20 years for some other blockchain. We don't know whether Namecoin will be abandoned for some other blockchain. We don't know whether these blockchains will be attacked, whether somebody will, invent a new kind of blockchain that has, new privacy features that these ones don't, and everyone moves to that, or is better in some other way. And even beyond that, to focus on one blockchain is, again, to centralize a distributed system. And that's not good, because with centralization tends to come abuse of power and cronyism and all of these other kinds of problems, which is what we're trying to get away from with Bitcoin. We're trying to get away from the trusted third parties who charge you arbitrary fees and freeze your funds and all of this nonsense. So that's what Bitcoin and decentralized systems make possible, is to get away from that. And to focus on only one of them would be to perpetuate that problem. Any questions?
What's the timing in terms of when you think you're going to get to this uber thin client? I mean, are you a year away from having all that data and being able to get there, or do you think it's imminent? I mean,
That's a good question. Well, we're going to be crowdfunding for doing this precise research. And that will help us simply pay for people's time to look into it. And we may or may not be able to do it, but we'll definitely push it forward a little bit. Optimistically, I'd say within a year, maybe even sooner. It really depends on the interest. If a lot of people are really interested in doing this, somebody else could do this on their own, and or work with us or whatever. So if there's a lot of interest, it could be a very short amount of time. If there's not, and we want to define essentially an RFC, an internet standard for this kind of protocol, and that process takes a while. So even once we fully define it, then you have to standardize it, get it into IATF. Chris isn't here, but he knows all about that. And I mean, do you know how long it took the internet to move from HTTP to HTTPS? I mean, we still even haven't finished that. But it was like, I don't know, at least 20 years just to move from HTTP to HTTPS. So, and certificate transparency is another problem that tries to band-aid the situation I was talking about earlier with certificate authorities. I mean, that's an effort that's been going on for several years already. So this is, I'm guessing this is kind of like, to create an internet standard takes a long time. And then to actually get implemented and adopted takes even longer. Okay.
Thanks very much.